Here comes an example of generating a Taylor polynomial for the function 1 over 2x minus x squared at the anchor point of x equals 1. I have the Taylor polynomial setup formula right here. However many terms we're going to go out to, 5, 8, 10, whatever, goes there and there. And then we need the derivatives of the function evaluated at the anchor point. The n factorial is hardwired. This term with the exponent is hardwired. However, we'll put in x0 equals 1 because that's our anchor point. So what we need here is a whole bunch of terms individually written. We need the derivative of the function of that order, and say the 0th derivative is just the function itself, which I will write like this for convenience and for derivative purposes. And then we need to find out what we get when we plug in the anchor point to that particular derivative. When we plug in the anchor point of 1 in for x to 2x minus x squared to the negative 1, we just get 2 minus 1, 1 to the negative 1. So that's a big fat 1 as our result. Okay, going to get this out of the way. And now let's go to the first derivative of this function. Well, let's drop the negative 1. We'll have 2x minus x squared to the negative 2 times the derivative of 2x minus x squared, which will be 2 minus 2x. And look what happens here when we plug in x equals 1 to fill in this third column. That term right there, the 2 minus 2x when x is 1, that's going to give us a 0, and that's multiplying everything else. Look at that. All right, let's go to n equals 2. Now we need the derivative of the first derivative. That would be hideous. Okay, so fair game when it gets this bad. Remember, there's a threshold. Below a certain threshold, you say, you know, I'll just do this by hand. It'll take less time than it would take to go on the computer and get things ready and use technology to help me. This one, it's probably worth going for technology. So I have Wolfram Alpha all set up with this problem. And I've done the first derivative of our function just to get things ready. D over dx of 1 over, not d over dx of, the derivative, of 1 over 2x minus x squared. So Wolfram Alpha has the work we've already done. But what I'm going to do here, just so you can see how it goes, is turn this into a second derivative by putting d squared over dx squared of that function. Now here comes the second derivative. Okay, now that's pretty terrible. That's a whopper of a first term plus 2 over the square of the original denominator. So on my writing screen here, let me click back to that. I'm just leaving some open brackets. I'm not going to try to write that in there. I'm going to think this through on the screen. Where's my cursor? Here it comes. Okay, our job is to plug x equals 1 into this. Now it's a hideous mess, but look at this numerator on the left. It's got a 2 minus 2x in it. When x is 1, that's a 0. That whole term goes away. When we plug x equals 1 into this term, we get 2 over 2 minus 1 squared. So that's just 2. So let's go back to our screen and write down the value of the second derivative at x equals 1 for this messy function is 2. And I'm just going to put WA for Wolfram Alpha. Let's try that third derivative. Let's head back for Wolfram Alpha here. Let's change this to a third derivative. And then we see on the screen the horrible third derivative of this function. However, again, when we plug in x equals 1, that term 2 minus 2x in the numerator appears in both of those messy fractions, which means both of those are going to turn into 0 when we plug in x equals 1. So back here again, we're not going to write that derivative down, but we do know that we plug in x equals 1, we get 0. Okay, let's try the fourth derivative. Update our derivative to the fourth. Ooh, this is going to be terrible. Oh, look at that. Gross. Okay, three terms now in our derivative. However, first term has 2 minus 2x, second term has 2 minus 2x. When we plug in x equals 1, those become 0. The only surviving term at x equals 1 is going to be this third term, and that's 24 over a quantity that when we plug in x equals 1 will just become 1. So back to our screen, I've put in a 24 in that spot. Okay, I'm going to take a crazy guess. Since the first derivative and the third derivative generate coefficients of 0, I'm just going to take a crazy guess that we will get 0 in that spot. So the next derivative, because I've got 1, I got 2, I got 24, I'm not really seeing the overt pattern there. However, if I start thinking about factorials, because factorials often wind their way in here, 1 is the same thing as 0 factorial. That's 2 is a 2 factorial. 24 is a 4 factorial. Now 6 factorial is, let's see, 5 factorial is 120, so 6 factorial is 720. So I'm going to say, is this going to be 6 factorial? Maybe? Well, let's go back to Wolfram Alpha. Let's leap right to the 6th derivative. Oops. And looky there. Okay, this is really hideous. 3 hideous terms that when we plug in x equals 1, they all vanish. And look at this 4th term. The numerator is 720, and the denominator, when we plug in x equals 1, turns into 1. So we've got it. Going back to my screen. These are the magic values, right? We've seen them work out. So what we're going to do is we're going to have to generate a series formula that when we have even values of n, give us 0. When we have odd values of n, give us that number factorial. So here's the trick. That thing in brackets, 1 plus negative 1 to the n, that is a quantity that will give me 0 for odd n, and will give me 2's for even n. But for now, the important thing is it'll be 0 for odd n. If I divide it by 2, now I've got a quantity that when n is odd will give me a 0. When n is even will give me a 1. These numbers here are n factorial for n equals 2, n equals 4, n equals 6. So let me make that product. That's what these coefficients are going to be. When n is 0, we'll get 1 times 0 factorial, which is 0. When n is 1, we'll get 0. When n is 2, we'll get 1 times 2 factorial. When n is 3, we'll get 0. When n is 4, we'll get 1 times 4 factorial. When n is 5, we'll get 0. When n is 6, we'll get 1 times 6 factorial. So boom, there's our coefficient, and I've used up the whole page, so here's our template. Continuing on to this page, our Taylor polynomial will look like n equals 0 to n. Okay, that much of it is just our coefficient. That much of it is this, what we just generated out of that table. When we're loading up our template, this now has to get divided by n factorial. How about that? And then x minus our anchor point was x equals 1 to the nth. Cancel, cancel. Get rid of this. And there you go. That is the general recipe for the nth order Taylor polynomial for the function 1 over 2x minus x squared anchored at x equals 1. Now, in a lot of problems, it'll say specifically, find the fourth order Taylor polynomial, which means go out to where you see an x to the fourth. Do the sixth order. If the problem specifies a particular order like 2, 4, 6, all you have to do is take this information and write out the terms individually into your polynomial. You don't necessarily need to collapse it all together into a formula, but I recommend practicing, because in the next section what we're going to do is say, well, now we want the Taylor series, meaning we want the Taylor polynomial allowed to go out to an infinite number of terms, and in that case you want the collapsed summation version of the Taylor polynomial so that you can just put an infinity right there at the top to have your Taylor series. So discovering the pattern is always a good thing, even if you didn't really need to. Let me show you what we've got graphically. In this window, the red curve is the 1 over 2x minus x squared. We know the red curve is that function. Well, I know because I know that the first curve in the plot is the red curve, but also because that function is going to have vertical asymptotes at x equals 0 and x equals 2. And that red curve is definitely showing those asymptotes. The Taylor polynomials cannot have a discontinuity, so they're going to try to make the function as good as they can, but they're not going to have asymptotes themselves. And so you can see that around x equals 1, where the right there at the thumbtack, where these two curves stick together, the blue Taylor polynomial approximation that goes out to x to the fourth here on the screen, at the region centered around that point, there's a pretty good approximation for like a half a unit in either direction, but then the polynomial says, never mind, and it goes on its merry way. If we started adding more terms to this, here, let me see if I can do this again. I'm going to do a series. I'm showing you the trick. I don't mind if you do this to check your work. Just make sure that you know how the result happens. What you can't see on your screen is when I selected series, a little window popped up for me asking me what expansion point do I want, which is 1, and how many, what's the order. Well, I put in a low order before, so this time I'm going to make it a larger order. Okay, so now I'm going out to x to the 10th. I'm going to cut out the actual polynomial part. That big O term, that's order of. That just means everything else that comes after this starts at x to the 12th and goes on. Whoops, it didn't copy well. I'm trying to copy all of this because it won't recognize it to plot it with that order of term on the outside. Okay, there we go. I just hit enter, and now my plot command has 2 new plots in it. We should see the region of expansion widen a little bit. Whoa, what just happened? Oh, I lost the 1. See, when I did my copy and paste, there's a 1 plus. There we go. Okay, that's better. I lost my 1. That's why my blue curve dropped down by 1 unit. That's better. Okay, now you can see the agreement between the two functions is much better than it was before. Also, I didn't do that on purpose, but that's a good example of knowing what it is you're looking at, knowing what to expect, so that if something goes wrong, you know it. I knew something was wrong because I knew that blue curve was supposed to attach to the red curve, and so I just had to go back and figure out what it was.